Hello, we are the learning group of our AI for Good project. So our learning group member include Asans, Haoqian, Kevin, and Wenxuan. So we are doing our final presentation of our term project. Fair opportunistic resource allocation, short for all. A food desert is an area that has limited access to affordable and nutritious food, and the scope of this project is to build a delivery and distribution system to help the people in food desert to meet their nutritional need and have a better living standard. The learning group main purpose is to determine the expected supply and demand vectors and the user preference priority matrix based on the prior knowledge and the feedback from the communication group. So our uh, useful matrix will be having the demographic data as also the explicit demand will be denoted as a matrix of X, which include items from X1 to Xn, and our food distribution center explicit supply will be denoted as a matrix of Y, which include Y1 to Yn. So for the communication group output defining the food item as I from I1 to Ims, we are defining our food item vector from A of I1 to A of Im, representing the explicit or available supply in the areas. So this is our um, architecture designs. So we are consider the allocation histories, the user demographic or explicit demand, the food distribution center explicit supply, and allocation from last time T minus ones, and as well as our priority normalizations and the priority of last times T minus one into our main component, the multitask learning component. This is a neural network. They will output the uh, parameters for two LSTM cells, which will generate implicit demand and implicit supply, which is our predicted value. So our priority and allocation history will be incorporated into our those two metrics. The first matrix is N matrix, where N of IJTs is for every I in I for every J in use. There is a priority of food group J to the user I at time t. So similarly, we have also the item matrix H, where HIJTs is for every I belongs to I, every J belongs to use. HIJT is the allocation of the item J to the user I at time t. So for our calculations of priorities, we are using this given equations here. So the priorities n of t is the priority of the user and item t at a time is calculated by the last time's predictions, the n of t minus 1s, and our nutritional value from the USDA data NVs, and minus the allocations of t minus 1s, a of t minus 1s, and the RQ is the user feedback on allocation. So subtract the means of the allocations, account for their always rated the allocation highest. The higher value of RQs means the user need were met, and we can lower the priorities for next times. So we are set those value to be no negatives. So if the user have a negative value, it means that their nutritional need are already met. So we are just putting 0 instead of negative value. And we all normalize all the value for all user in times t's. So for our priority prediction algorithm, we decided to use AdaBoost. The purpose of AdaBoost is to determine a person with the greatest priority at times t given a matrix C of priorities for all user items for t minus 1. So our approach is to choose a classifier that minimizes the total weighted error and calculate error rate at each step and calculate ideal weight and use it to improve the classifier. So our current model is struggling because we have incomplete matrices. So we added 0 values in place of the missing data, which are causing higher error rate and will be resolved when all the matrices are calculated. So the figure on the right is detailed step for our algorithm to work. So we are also using the LSTM with multi-task learnings. So in our approach, we assume that food delivery system is just another agent that taking our food allocation recommendations as input. So we also assume that the explicit supply consists only of the explicit supplies. Since incorporating the wrong pair for the implicit supply can have devastating effect on our model's performance. So every food desert person will sign up and regularly use their applications. So we'll input our explicit demand and explicit supply and priority for T minus one and allocation for T minus one and allocation history into our MLP component, which is a neural network that output the desired parameter for both LSTM for our demand and LSTM for our supply, which will generate our predicted result of implicit demand and supply. So this is a detailed design for our each of the LSTM cells. So since we are stated in last work, only we're taking account in the supply, it's the supply from last time, because if we are incorporating the wrong one will have devastating effect. So only the input in our demand cell, a supply cell, is the supply from last time. But for our demand, we are incorporated the priorities, the last time's demand, allocation, and allocation history together to produce the implicit demand output. So for evaluation our systems, our performance of the LSTM or any ML model, we rely on the patterns in our data. So if the input data does not have any patterns, we cannot get a good predictions. So let's visualize some survey responses. So this response is our input visualizations. We can see this is their demand at each given time for different users. So we can see a lot of users desire 0 items at some times, like here the blue line has no desired items, and here we can see also some people desire 0 items at the days. So for when we do our explicit demand for users, we can also see like kind of patterns in our models. So we can see for some times t, we don't have the item allocated to a person, so we are now giving the item to a person who don't want it. So we are eliminated. We are just solving the waste problem for unwanted items. So this is the average explicit demand for our fruits. So we can see the explicit demand will be the growing then decreasing, which is the feed pattern of the input. So this is the experimental result for explicit supplies of orange. So we can see for every different users, the supply will be different. And this is the explicit supply of a user for different kind of fruit and a different kind of rice and different kind of nutritional food. So we can see they are vary a lot for each users. So in our result, we can see the average explicit supply also varies according to their input. So we can see they're the same patterns here. So for our without allocation and feedback for items orange for the user, we can see the items predicted demand and true demands are different. So they only have a lags of here and here's. The predicted demand will play a catch up to catch the real demand, true demand. So we don't want to do that. So we are taking account the priorities of users. So we can see this as the initial priorities for different types of items. And we can see for the items here, we are allocating different uh, type of fruit to different of people. So we can see because in our USDA need, the fruit has a lesser weight than the rice and oats. So we are allocating oats and rice to those two users, and we're allocating a little bit of the priorities to the fruits such as orange, apple, watermelons, bananas, and eggplants, and the tomatoes. So with the allocation and feedback, we can see the gap between the predicted demand without the feedback and the predicted demand with the feedback t minus t equals 2. We can see the predicted demand with the feedback of the t equals 2 has a better consistency with the true demand. So which means our priority prediction works. And for the limitations on the future direction for our work, we are only relying on the allocation data from the decision-making group, and we are also have some possible some work towards to a unified approach because we are currently limited to our group and other group. If we can combine a system as total, we can take each step of their work into our input so we can have a faster and more responsive system in the futures. Thank you. This is all of our presentations. Any questions?